Welcome to Lecture 22, Calculating Determinants, the wonderful determinant, and how to calculate it. So we're going to start off with the definition of the determinant. The determinant of a matrix turns out to be one of the most important objects in linear algebra. We're going to start by defining it, and then we're going to infer some of the properties of the determinant, and then finally we're going to look at some examples for how you can actually calculate it. So the determinant of a matrix A is given by the following formula. I have to find all permutations P of n objects. I'm going to multiply by minus 1 raised to the power P symbolically. What that means is if it's an even permutation, that number is 1. If it's an odd permutation, that number is minus 1. And then I look at a product of the different elements of A P1, 1, a P2, 2, a P3, 3, and so forth, all the way down to a Pn, n. There are n factorial terms in this sum, and each of those terms involves a product over n matrix elements. One element in the product comes from each row, and one element comes from each column, and no rows or columns are repeated. Okay, so P1 through Pn is a permutation of 1, 2, 3 all the way out to n, and minus 1 to the P is 1 if P is even, and minus 1 if P is an odd permutation. Now, you might ask, how do you decide whether a permutation is even or odd? What we have to do is we have to construct the permutation as a sequence of pair exchanges, and if the number of pair exchanges is even, then the permutation is even, and if it's odd, then the permutation is odd. And as an example of how this works, consider how I got to consider going from 312 to 123. So the first thing I have to do is I have to interchange the 1 with the 3. That'll take me from 312 to 132, and then I have to interchange the 2 with the 3. So I go from 132 to 123, and you can see that involved 2 pair exchanges. And so it's an even permutation. And there are many other numbers of pair exchanges I can put in, but no matter what way I try to do it, it always will be an even number. So I can do it with 2 pair exchanges, 4 pair exchanges, 6 pair exchanges, etc. It's always an even number. And so that's why we can define this as an even permutation, and that's a well-defined object. Now, there are n factorial permutations of n objects. Half of them are even and half of them are odd. And so this formula for the determinant is really difficult to use for large matrices. If I have a 10 by 10 matrix, I have 10 factorial terms, and that's just a huge number to try to evaluate. But it actually is a pretty useful formula for small matrices. So let's just look at a couple of examples for small matrices. So if n is equal to 2, then the determinant is just a1, 1, a2, 2, minus a2, 1, a1, 2. And where that comes from is 1, 2 is an even permutation, and 2, 1 is an odd one. So the odd one gets a minus sign, and the even one gets the plus sign. For n equals 3, it's slightly more difficult, but we can work it out. There's 6 permutations here. And these are all of the different contributions that come out. And we have ordered these 6 in the following fashion. The first one is the permutation 1, 2, 3, which is even. The second one corresponds to the permutation 2, 1, 3, which is an odd permutation. The third term is the permutation 2, 3, 1, and that one is even. The fourth is the permutation 1, 3, 2, and that one is odd. The fifth is the permutation 3, 1, 2, which is even. And finally, the sixth is the permutation 3, 2, 1, which is odd. And that incorporates all of the different 6 possible permutations of 3 elements. All right, so let's take a look at some properties of the determinant. And first, we're going to rewrite the definition for the determinant in the following form. We're going to introduce this new object, epsilon sub P1, P2, P3, all the way out to Pn. And that object is going to equal 1 if the permutation is even. It's going to equal minus 1 if the permutation is odd. And it's going to equal 0 if any 2 of those indices are the same. And then that allows us to sum freely over all of the indices P1 going from 1 to n, P2 going from 1 to n, and so forth. So if a row of A is all zeros, then the determinant of A is equal to 0. So let's see, how do we prove that? Well, I told you before that one element from the row of zeros is going to appear in every product of terms in the summation. And so since one of those is guaranteed to be 0 because the entire row is 0, then every term is 0, so then the determinant is also 0. And this exact same argument holds if we look at a column of zeros as well. The second property is if a row is multiplied by lambda, then the determinant is multiplied by lambda. And this also holds for similar reasons. Since there's one element from each row or one element from each column that appears in each of those products, that element is going to get multiplied by lambda, which means each one of those products gets multiplied by lambda. So each term is multiplied by lambda, and I can factor that out. And then the entire determinant is multiplied by lambda. And as I said, the same thing happens if we multiply a column by a factor. All right, that's good. We have a couple more properties we're going to look at. If two rows or columns are interchanged in the matrix, then the determinant changes sign. And the proof of this is pretty simple as well. The interchange of a row is the same as adding one more pair exchange to each permutation. That pair exchange would be the pair exchange that exchanges the two rows that we're exchanging in the new matrix. And by adding one pair exchange, I change all even permutations to odd and all odd to even. And so the net effect is that every one of those terms gets changed by multiplication by -1. And so the entire determinant changes sign. So if I interchange two columns, the determinant will change sign. Now, the next property is one that at first might seem difficult to prove, but if two rows are proportional, then the determinant vanishes. And it turns out this proof is also fairly easy to do. What we do is we're going to multiply one of the rows by a factor so that the two rows become identical. Now, if I have two identical rows, if I interchange them, the matrix doesn't change, so the determinant can't change. But by the property number 3 that we just showed, the determinant does change sign. So we learned that the determinant of A is equal to minus the determinant of A. Well, that can only hold if the determinant is 0. And so if two rows are proportional, the determinant will be 0. And this will also hold if two columns are proportional as well. All right, we're moving right along. The next one we're going to prove is that if I can separate a particular row, Aij, into Bij plus Cij, then if we define the matrix capital B to be the same matrix as A, except we replace the ith row by the vector B, and I do the same thing for C, it's the same matrix as A, except I replace the ith row by the vector C, then determinant of A is equal to determinant of B plus determinant of C. And the proof of this, also fairly simple. Every place an AIX appears in the determinant formula, we replace it by BIX plus CIX. Now this term will appear once and only once in each of the product terms in the definition of the determinant. So I'm only going to get one of those factors in each of the terms. We're going to group all the B terms together, and we're going to group all the C terms together. And then just by the definition of the determinant, you immediately see determinant of A is equal to determinant of B plus determinant of C. And of course, this argument also holds if we did the same thing for columns. Okay, our sixth property, if we take the ith row or column of A and multiply it by a number and add it to the jth row or column, then the determinant does not change sign. It does not change its value. All right, how do we prove that? Well, let's take the matrix B and set it equal to matrix A, and we can think of that as picking the column vector B to be the column vector A. And let's take matrix C and construct it from A, but replace the ith column of Ci with the jth column, the ith row of the matrix A with the vector Cix that we're going to choose to be lambda times the jth row of A. Now, because we know the determinant of the sum of those two matrices is going to be the sum of the determinants of those two matrices, that's the property we just established, then after I do the addition on these two rows, I'm going to find that the determinant of that final matrix is just the determinant of B plus the determinant of C. But we know the determinant of C is equal to 0 because two of its rows are proportional. And so we immediately learn that the determinant of the original matrix A and the determinant of the new matrix that we get by taking a row, multiplying it by a number, and adding it to a different row, that those two determinants will be equal to one another because the determinant of C is equal to 0. And of course, this same thing will hold if I look at two columns. All right, our seventh property, the determinant of the transpose of the matrix is equal to the determinant of the matrix. And so that says determinant of A is equal to determinant of A transpose. Remember, the transpose of the matrix interchanges the rows with the columns. So we write Aij transpose equals Abi. And so we're interchanging what is a row and what is a column. If you like, it's a reflection of the matrix about the diagonal. Now, it turns out the determinants are the same because we can always rearrange a product AP1, 1, AP2, 2, AP3, 3, etc. into A1, P1, A2, P1, A3, P3, etc. by reordering the terms in that summation. And the one thing that you have to check is how does the parity of that permutation change? And it turns out that it doesn't. The parity of the permutation remains the same when I do this interchange, and so the determinant remains the same. All right, moving right along, there's another way that we can calculate the determinant. It's called an expansion by cofactors. We have to first define what a cofactor is. So the ij cofactor of a matrix, which we call C sub ij, is defined as minus 1 raised to the I plus j power times the determinant of the matrix formed from A by removing the ith row and the jth column. So whenever I do this, I actually like to take a line and draw a line through the ith row and the jth column, and then I just pack everything back together in the matrix in such a way that I have a matrix now that has a dimension of n minus 1 by n minus 1 if I started with a matrix that was an n by n matrix. Okay, now the claim is that the determinant of A is then equal to the sum over J. This is going to be summing over columns, Aij, Cij, or it's equal to the sum over I, Aij, Cij, where I'm then summing over rows. And this ends up being a very useful way to calculate a determinant if one of the columns or one of the rows has a lot of zeros in it, because then a lot of those Aij terms are 0, and you find that the determinant ends up being just related to the sum over these cofactors. Now the proof, you just have to think carefully about it. It actually is just a rewriting of the definition of the determinant, and so it's really a very straightforward thing to establish this proof. Okay. Our final property, if C is equal to A times B, and that means matrix multiplication, so Cij is the sum k equals 1 to n, Aik, Bkj, then the determinant of C is equal to the determinant of A times the determinant of B. And in some sense, this is one of the most remarkable properties of the determinant, and let's take a look carefully at the proof of this. So the determinant of C is just this completely antisymmetric tensor, epsilon p1 to pn, and CP11, CP22, all the way out to CPNN. And now we're going to substitute in what each of those C elements are in terms of the sums of AP1, K1, BK11, and so forth. And at this point, we're just plugging in the definitions of everything. We haven't done anything fancy whatsoever here. We're going to regroup all of those sums, pull them all the way over to the left, and the claim is the sum over p's is going to give me the determinant of A almost. If you look at the left-hand side here, it's the determinant of A times epsilon k1, k2, all the way out to kn, because if it was the determinant of A, it would be A p11 and would be A p22, but we have A p1k1, A p2k2, and the way that I will interchange between k1, k2, kn to 1, 2, 3, all the way out to n is going to be either an even permutation or an odd permutation. And so I have to take into account that minus sign by adding this factor epsilon k1, k2, k3 all the way out to kn. So because the determinant of A is, or because that sum over epsilon is equal to this determinant times that antisymmetric tensor involving the k's, I find after I do a sum over all those permutations p, I'm left with a sum over all the permutations of k of bk11, bk22, all the way out to bknn. That's just the definition of the determinant of B. So I end up getting determinant of A times determinant of B. And in my opinion, this is one of the really miraculous identities that you get from looking at properties of determinants. Okay, we've gone through a lot here. This has been a long lecture. It's probably one of our longest lectures. We've discussed a lot of these properties, but until you actually start using them, you really don't internalize them and feel comfortable using them again. And so we're going to start by doing a couple of examples, but of course we're going to do more of them in class and in the different laboratories that we're going to be doing associated with linear algebra. So let's look at a couple of quick examples. We're going to be looking at the determinant of a 3x3 matrix, and I know all of you have probably memorized the formula for how you calculate it by drawing the different kinds of diagonals. We're going to evaluate it in a slightly different way. We're going to use row reduction. I'm sorry, we're looking at a 4x4 matrix, not a 3x3. So most of you don't know exactly what the formula is for doing this. And so we're going to do row reduction. And at the end of the row reduction, we're going to be able to read off what the determinant is. So it's going to take me a couple of steps to get there. So we start off here. We look at the first row. We're going to be maintaining the first row, doing nothing with it. We now look at the second row. We see that there's a 3 in the first element, and there's a in the second row, and there's a 1 in the first element of the first row. So I have to take the first row, multiply it by 3, and subtract it from the second row. And so I'm going to then get 3 minus 3, which gives me 0. I'm going to get 5 minus 6, which gives me minus 1. I'm going to get 1 minus 9, which gives me minus 8. I'm going to get 0 minus 12, which gives me minus 12. Now for the third row, I don't have to do anything. It already has a 0, so I just copy that row. And then for the fourth one, you see I have to subtract row 1 from it. So I get 1 minus 1 is 0. I get 1 minus 2 is minus 1. I get minus 2 minus 3 is minus 5. And I get 3 minus 4 is equal to minus 1. All right, that's our first stage of the row reduction. Now we look at the third row. You see I've got a 2 there. And if I look up into the second row, there's a minus 1. So I have to multiply the second row by 2 and add it to the third row. So I'm going to get 2 minus 2, which gives me 0. I'm going to get 6 minus 16, which gives me minus 10. And I'm going to get 0 minus 24, which is going to give me minus 24. Now when I look at the third row, what I'm going to have to do is the fourth row, I'm going to have to subtract the second row from the fourth row. So I get minus 1 minus minus 1, that gives me 0. I get minus 5 minus minus 8, that gives me 3. I get minus 1 minus minus 12, that gives me 11. So now we have this matrix that's the third matrix that's given here, and we have one more row reduction we have to do. I have to take the third row, multiply it by 3/10, and add it to the fourth row. So I will get 3 minus 3, which gives me 0, and I'll get 11 minus 7.2, which gives me 3.8. And then we get our final matrix. And you see we've constructed this nice triangle of zeros in the lower left-hand corner. We still have the diagonal present. And that is enough now to determine the determinant of this. And how am I getting this determinant? Well, essentially I'm starting with the first row and evaluating by cofactors. So the first row gives me a 1, and then I have the cofactor, which is the 3x3 matrix below that, and then I evaluate that by cofactors. It gives me a minus 1, and then the 2x2 matrix is the lower one. I evaluate that by cofactors, I get a minus 10, and then I'm just left with a 1x1 matrix, which is the 3.8. And if you notice, what this does is I actually just take the product of the diagonal elements. So whenever I've got a matrix in the row-reduced form, all I have to do is take a product of the diagonal elements, and I will get the determinant. And so let's do that. I get 1 times minus 1 times minus 10 times 3.8, and I find out that the determinant is 38. Now, since this matrix is a matrix of integers, it's a fairly simple proof that the determinant must be an integer if the matrix is a matrix of integers, because all of the terms in the definition of the determinant are integers. And so it's comforting to see that this determinant does come out to be an integer. All right, let's go ahead and calculate the original matrix in terms of cofactors. We're going to use the last column, and we're going to go by cofactors. So I have a 4, and it's going to be times -1 because I plus j is an odd number. And then I have the determinant of the matrix where I cross off the row and the column, and that's just 3, 5, 1, 0, 2, 6, 1, 1, -2. And then the other cofactor is going to be a 3. This one is an even one. If I add the I plus the j, I get an even number, and take the determinant of the matrix I get by crossing out those rows and columns. And that's the matrix 1, 2, 3, 3, 5, 1, 0, 2, 6. Now I just use the formula I know for the 3 by 3 matrices to calculate the determinants. And the individual terms are written down for you inside those parentheses. I go through all that algebra, and I find that I get 8 plus 30, or 38, which of course agrees with the answer that I had gotten before. And so indeed, this is the correct answer for the determinant. And that ends the examples that we're going to go over in this particular lecture.